Now let's look at Turing machines. So before talking about the theory about Turing machines, my concept is always straightforward. I'll take examples, lot of them, and I'll explain all the examples first, and then let's get into the theory. So even if I talk about Turing machines in theory, you will not be able to understand anything. So I'll just take an example and I'll explain you few examples, then we shall move on to the theory. So Turing machine. So what is the main difference between Turing machine and other machines like push-down automata and finite automata is, till now we have seen that either push-down automata or finite automata, it moves in only one direction, from left to right. But then Turing machine can move in both the directions. That is one difference. And second thing is, Turing machine can even read a symbol from the tape as well as write on it. So a Turing machine will have something called as a tape, and on the tape input will be present and there will be a read write head. So Turing machine will have finite control, and using this read write head it will read the symbol on this and it can even write on it. For example, I'll just design a small Turing machine which will be able to accept a power n, b power n such that n is greater than or equal to 1. And remember that Turing machine is not capable of accepting epsilon. The reason is Turing machine, okay, I'll tell you that later, but for now understand that Turing machine cannot accept epsilon. Therefore, I am taking a power n, b power n, n is greater than or equal to 1. It rarely, it doesn't make any difference whether you include epsilon or not. It doesn't really make any difference. So let's keep it simple. A power n, b power n, n is greater than 1. This is the language given. Now we have to design a Turing machine which is going to accept this language, a power n, b power n. First of all, is this language regular? It is not regular. Is it context free? It is context free. We have even seen a grammar which context free grammar which is used for this, and we have even seen push down automata how to design it. Now let's see how the this Turing machine work on it. So I'll take an example. Let us say a power n, b power n, n is greater than or equal to n. One of this string is a, b, b. If this is present in the tape, what happens is, on the tape you will be given the input, and to the left of it there will be blanks, all blanks, and to the right of it there will be all blanks, and your Turing machine will be pointing to a symbol in the input like a, right? So how Turing machine works is, just to take an analogy and explain you could think of Turing machine as a man who doesn't know how to count. So let us assume that a man doesn't know how to count and he is supposed to count now. So just assume like this: there are two rooms. Okay, there are two rooms, and in one room there are bags of cement, and in other room there are bags of sand. And now you are given, there is a man here and he doesn't know how to count, and he is given the responsibility to cross check whether the number of bags of cement are equal to the number of bags of sand, and he doesn't know how to count. Then how is he going to do that? One possible answer you might come up with is, pull out one bag of sand outside and one bag of cement, and one bag of sand, one bag of cement, one bag of sand, one bag of cement. Pull them out and pair them up, it is done, isn't it? Yes, we can do that. If he doesn't know counting, obviously he has to do all that labor, right? He has to pull out every bag and then match them. But then can he do something better? Which means without pulling or moving these bags, can he do something better? Yes, one thing is simple. He can take a stone, a brick, a small or a chalk, and he can go to one room and mark on this, and then he can go to other room and mark on this. Again he can come back, mark on this, come back, mark on this. So he can keep on marking one here, one here, one here, one here. If we do that, then it is nothing but comparing, isn't it? So the same way our Turing machine will also act the same way. So it has the capability to read a symbol and then change that symbol, move left as well as move right. These are all the functions which a Turing machine can do. So Turing machine is capable of reading and then changing means writing on it, and then moving left and moving right. Okay, so what it will do is it will see A and mark it as seen, which means it will make it X, and then it will keep on moving right, and whenever it sees a B it will make it Y and then keep on moving left, and again the next A it will make it X and again keep on moving right, and next B it will make it Y and keep on moving left, like this. So every A will be marked as X and every B will be marked as Y. So if you didn't understand it, I'll take one more example. See this. Let us say A, B, B, B is given to the Turing machine, and on either side there are simply blanks. There is nothing but blank. Okay. Now how a Turing machine works is, it will look at first A, make it X, and then go right. Look at first B, make it Y, and then go left until it reaches the first X. It ensures that we are standing just behind the unmarked A, first unmarked A. So you go left until you reach X. After you reach X, you turn right and make it X, and again go right and cross all the A's, cross all the Y's, and then reach B and make it Y, and again go left, crossing all the Y's and crossing all the A's until you hit the first X. After you hit the first X, move right and make it X, and again you keep moving right until you hit the first Y. On the way you might get any number of A's and any number of Y's. Leave them and then make it Y, and again keep moving left until you reach the first X. And after first X, if there is no A, if there is simply Y, what does that mean? It means that all A's are over. Now make sure that all B's are over or not, which means go to the right and see if all B's are over. If all B's are over, you can say that yes, it is accepted. All A's are followed by all B's, right? Now let's write the Turing machine. I'll just write the transition diagram for Turing machine and explain you this in a easy way. So in order to construct this, taking an example and doing it will be very easy. I found out that it is very easy to explain you by taking an example. So let me say I have A, B, 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 and to the left there are blanks, and to the right there are blanks, and there are lots of blanks. Okay, and now I'll start assume that in state Q0. In state Q0, what happens is I'll see a. If I see a, I'll replace it with X, which means I'll replace it with X, and I'll move right. Right means I'll go to the next symbol like this. Okay, and after moving right, what my purpose is, I have to search for 1B and make it as Y. So in Q1, the purpose of this state Q1 is to find the next B or the first B. So it will keep on moving. While moving, what it could see is any number of A's, leave them all as A's, and you keep moving right. So it helps if I extend this, if I trace this example 2 more steps and then show you, because it will help you. Let us say the B is found and it is made Y, and again we are here and now it is made X. Okay, now we are here, so again we will be in state Q1. Now it will help you. See this. Now after making A as X, and when you are searching for Y, on the way what you could get, when you are searching for B, on the way what you could get is any number of A's. Therefore any number of A's you can get, leave them as A and keep moving right, and then you can get any number of Y's. So before you get a Y, second B, you might get any number of Y's. Therefore as long as you see Y's, leave them as Y's and you keep moving right. Understand this? Whenever you have made A as X, and when you are searching for a B, on the way you might get any number of A's or any number of Y's. So you leave all the A's as it is and you leave all the Y's as it is, and you keep moving right until you hit the first B. So whenever you hit the first B, that is where you make that B as Y and you start moving left, which means you make this B as Y and again you start moving left in search of first A. So in order to search the first A, you should search the first X. Therefore when you are moving left, you are actually searching for X. So once you search X, when you are here, and when you are moving left like this, once you hit x, then the symbol next to it is a. That is what you wanted. Okay, so now you will be in q2, state q2. When you are moving left from here, you may get any number of y's and any number of a's. So you might get any number of y's, leave them as y and keep moving left, and you might get any number of a's, leave them as a's and you keep moving left, and finally you might hit the first x. So whenever you hit the first x, the history repeats, which means whenever you hit the first x, if it is x, leave it as x and you move right, which means you will be standing at this point. And again entire thing will repeat. What is it? Make a as x, make a as x and you move right, and as long as you see y's, leave them as y and keep moving right. And whenever you see a b, yes, whenever you see a b, you make it as y, and you keep moving left, and when you are moving left, you may get any number of y's, and finally you will see a x. Therefore whenever you see a x, you are here. Now after x, you are supposed to see a if there is a present, but then if all a's are already marked as x, all a's will be over. If all a's are over, how do you know that all a's are over? After ax, you will immediately see a y. Therefore there should be one more path. So what does it indicate? After ax, you are seeing y. So what does this mean? All a's are over. So should I stop here and accept it? No. I should even check whether all b's are over or not. The reason is 3 a's will be there, but 4 b's might be there. So you should even check whether all b's are over or not. If all b's are over and all a's are over, then only you can accept it. Therefore I just want to make sure that all b's have been marked. So if there is a y, I'll leave it as y and I keep on moving right. So when I'm moving right, what am I supposed to see is only y's. So as long as I see y's, I keep on moving right. Any y I see, I leave it as y and I keep on moving right, and finally all the y's will be over. In case if all the y's will be over, and if I see a blank, then you can leave it as blank, you can move left or right, no problem, and finally you can accept it. What does this mean? It means that q0, okay, let's number them, q3, q4. Just see what has happened. Initially you started with a and you marked it as x and you kept on moving right. When you are moving right, on the way there can be any number of a's or any number of b's, and finally you might see a b. And when you see a b, mark it as y and you keep on moving left. When you are moving left, there can be any number of y's or any number of a's, but keep on moving left. And then what happens is, finally when after seeing this first x, if you see a, it means that there is one extra a, then you go in the search of one extra b. Or in case after seeing the x, if there is no a, if there is directly a y, what does this mean? That all the a's are over. If all the a's are over, then what should you do? You should even check whether all b's are over or not. So I am going like this and I am checking all the y's. If all the y's are, if there are only y's, then I'll keep on moving right, and finally if I see a b, blank. So when I see a blank, it means that there are no b's. Therefore I am going to accept it. So this is how the Turing machine works. So again I'll take an example and explain you how this one is working. See, a, b, 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 and then there are blanks, blanks, blanks. So just see if you understood this or not. I made this one as x and then I kept on moving right. When I'm moving right, I can get any number of a's, and finally I see a b. Then I made it y and I kept on moving left. When I'm moving left, I can get any number of a's, and finally I hit a first x. And then after that, immediately I turn right. See this, after seeing a first x, I immediately turn right, and if I find a, the entire procedure repeats. What is the procedure? Make it x, make it y, make it x, make it y. That is how this one is working. Now there is something called as dead configuration. Dead configuration means I am expecting that, okay, if everything goes on well, which means if the string is in the format of a power n, b power n, then everything will follow exactly, or everything will fall in place. But if the string is not in the language, then something unexpected might happen. One of the things which is unexpected is, A, B, B, B. This string is not in the language, which means we are not expecting one extra B here. We are expecting only 2 A's followed by 2 B's, isn't it? There is one extra B, that is unexpected, right? Then how is our Turing machine going to answer this one is, it will take make it X, keep on moving right, make it Y, keep on moving left, make it X, keep on moving right, make it Y, and when it comes here X, immediately X will be followed by Y, which means after seeing a X, immediately it will be followed by Y. Therefore this path will be taken, right? And now in this path, in this one, so when it is taking this particular path, the problem is, check this, we are going to check whether every symbol is Y or not. So here the transition defined in Q3 is, as long as you see Y, you are making it as Y and you are keeping right. And if you see a blank, these two are defined, which means once you reach here, you are going to see only Y's or only blanks, and suddenly you will see a small b. So you will be in state Q3 and you will be seeing a symbol small b, but nothing is defined there. That is called dead configuration. If the string is not in the language, then you are going to hit dead configuration. Therefore the Turing machine will halt in Q3, which is not a final state. Therefore you can say that string is not accepted. So if a string is present inside the language, our Turing machine is going to hit the final state and halt there. Generally final state will halt. If the Turing machine has seen a string which is not in the language, it is going to halt in a different state because of dead configuration, right? So because of dead configuration, we are going to stop here. So we need not define every configuration like in DFA. In DFA, we are going to say for every state what happens on every symbol. But then here we are actually using it as a kind of not non-determinism. Non-determinism means from one state, if you go to two states on the same symbol, it is non-determinism. It is incomplete determinism, or it is deterministic only, but then we are not defining every possible configuration. Therefore, if there is any configuration for which we are not defining the transition, it is called dead configuration. And whenever our Turing machine hits such a dead configuration, we are going to halt in that state. So when our Turing machine halts here, we can say that the string is not accepted. And one more input which you could guess, which is not in our this symbol is language is A, B, B, blank, 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 blank. So what is the specialty of this input? Number of A's are greater than number of B's. Then what happens is, initially this will be made X, and again you will keep on moving right. Initially this will be made X and will keep on moving right, and then this will be made Y and will keep on moving left. This will be made X, this will be made Y, and then this will be made X, and now we will be in search of B, which means after making a as X, we will be in this state and we are in search of small b. So we will be looking at all the A's and we will be looking at all the Y's. We will be looking at all the Y's, and now we want to see a small b. Suddenly, instead of seeing small b, we will hit a capital B, which means in Q1 for capital B it is not defined. Then what can you understand? So since capital B is not defined for Q1, it is a dead configuration. Therefore, if for such an input, the Turing machine is going to halt in Q1. So either if A's are greater or B's are greater, Turing machine is going to halt in a non-final state by hitting something called as dead configuration. Then you can understand that, oh, it is dead configuration and you are not supposed to accept it. In case if the string is in the language, Turing machine is definitely going to go to the final state and halt there, right? So anyway, whenever you give any input which is not in the language, this is an example of a Turing machine which will definitely halt, but some Turing machines may not halt, okay? But anyway, here in this example, what I mean to say is, if the input is given and if the input is in the language, the Turing machine halts in final state, otherwise it halts in some other state. It need not be in Q1 and Q3 only, it can be anywhere, it can be Q2 or anywhere. So if the input is starting with, let us say, small b, let us say input is BA, then what happens? Q0, it is expecting to see small a or capital Y, which means it is expecting to see small a only, but suddenly small b has come, therefore it halts here, right? And let us say here when we are moving left, something unexpected might happen, and then you might halt there. So there are various conditions in which we are going to halt in a non-final state. So whenever the string is not in the language, we will halt in a non-final state. Okay. So I'll take more examples and explain you what with this.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So, first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%, and universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkee's ranking is 400. If you are happy to get into IIT Roorkee, then getting into universities better than IIT Roorkee is easier compared to getting into IIT Roorkee. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities, but whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.